Okay, congruent and similar triangles. Our learning goal for today is to investigate the relationships between corresponding sides and angles in pairs of congruent and similar triangles. And before we get into anything like that, let's kind of recall some of the angle properties that we learned in grade 9. Now, if you wanted to pause the video right here and maybe use maybe use this word bank and try to complete the blanks below, I think that'd be a great idea. If that's something you might have not wanted to do, then you can just stick around and we'll go through this together. Now, angle properties. When two lines intersect, the opposite angles are equal, right? We call these opposite angles. Like angle A, like these two angles would be equal to one another. And same with the B's. They would also be equal to one another. Also, in this type of triangle, if we have a look at this triangle, what type of triangle is it? It is an isosceles triangle. But that's not really what this is about. I mean, that was the blank. But we also, we know that an isosceles triangle, the two side lengths are equal to one another. But that being said, it says the angles opposite the equal sides are equal. So like this angle down here is the same as this angle down here. They are also equal to one another. Okay, this one down here, this is the blank is the sum to 180 degrees. So we have this straight blue line here and this kind of curved or slanted pink line. We have angle C, which is obtuse, and angle D, which is acute. And if we add them together, we get 180 degrees. This is what we call supplementary angles. Very similar to that, but a little bit different. We have a 90-degree angle, and we have E plus F equals 90 degrees. We call this complementary angles. Lastly, the sum of the blank in a triangle is equal to 180 degrees, while the sum of the interior angles. I mean, some of us might just say the sum of the angles in a triangle is 180, but really we should be a little bit more specific and say interior angles because there are such thing as exterior angles, but we're not going to get into that. Now down here, these last three, the Z and the F and the C, you might remember this from maybe even grade 8, grade 9 for sure. It says here, when a transversal, which is the blue line is what we call the transversal, crosses parallel lines. So the parallel lines meaning the pink lines that we have there, the two double-dashed pink lines. Many pairs of angles are related. So if we have a look at this first one here, you might look at this and say, oh, that's the Z pattern. And in the Z pattern, this angle here in the armpit of the Z is equal to this angle down here and the other armpit of the Z. But really, we shouldn't call it a Z pattern. We should really call it alternate angles because that's what they are. They're alternate angles, and we get them by, and a lot of us are so addicted to it, the Z pattern. Even myself, I find myself saying it a lot as well. Even this F pattern, we know that in the armpit of the F and the armpit of the F, we have those equal angles. Now, the F pattern doesn't just exist in this sort of orientation. You might even see one going upside down, right? You might even see one going backwards, right? And I know you've done this many, many times in grade 9, and we love it. It's good. It's really good. The F pattern, it's an important one. We shouldn't call it the F pattern. Instead, we should call it corresponding angles. In this last one, it rarely came up, but when it did, we're like, oh, okay, it's one of those ones, all right. And we call it co-interior angles. It's the C pattern, and it's basically A plus B. So this angle up here plus this angle down there, see that C pattern that's going on, we call them co-interior angles. Now, out of all of these definitions, this one I know you know for sure, and that's a good one to know for this unit. This one over here too, it might have slipped past you, but when you see it, you're like, oh yes, yeah, I remember that. The opposite angles. Also, alternate angles will come up. Corresponding angles will come up. And the rest of them, you might see them here and there, but not as often as the 4 that I have a star beside. Okay. Let's move in to congruent triangles. What are congruent triangles? Well, let's get a definition down. It's a pair of triangles that have equal corresponding angles and, so maybe I'll get my highlighter out here, equal corresponding angles and equal corresponding side lengths. Interesting. So if we have this example, it says here, for example, triangle ABC is congruent to triangle DEF. So we have the two triangles here. Let's just say in triangle ABC, we got 40 degrees, 70 degrees, and 70 degrees. And we also have, let's just say, let's just pretend this is an isosceles triangle. It's blue. So let's just say like this is 12, this is 12 units in length, and this is, I don't know, 8 units in length. If this is true for triangle ABC, then it must be the same for triangle DEF because the question states, or the example states, that they are congruent. So if you look at just this orientation of the triangles, we know that angle A, right up here, would correspond to angle F. So that would mean this angle up here would be 40 degrees, right? Angle A doesn't correspond to D, and it doesn't correspond to angle E. It would only correspond to angle F because they're both kind of in the same orientation. They're in the same spot on the triangle. Now down here, if B is 70 down here, then D must also be 70. And if if C is 70 down there in the bottom right, then E must also be 70, right? And that's because, right, we know A corresponds with 40, A corresponds with F, so that's why they're both 40, right? Angle B corresponds with angle D. And lastly, angle C corresponds with angle E. So that's what we mean when we say equal corresponding angles. Now, side lengths. If we're looking at side lengths, we can tell that side length AB corresponds, like this AB over here on this left side, would correspond with FD. So because they're congruent triangles, this one would also have to be 12. Likewise, AC or CA, whatever you want to call that side length, would correspond with EF, 12. Lastly, down here, BC or CB corresponds to DE, which is down here, which means this one must be 8. So some might say, all right, angle A is equal to angle F. Lovely. Angle B is equal to angle D, or corresponds with, yeah, it's equal to. Angle C is equal to angle E. And these are all the equal corresponding side lengths, right? Now, how about the sides? You know, AB, we said, corresponds and is equal to FD. BC, which is at the bottom, corresponds with DE. Now, some people ask, is it BC or is it CB? I mean, we know what you're talking about. It's almost like tomato, tomato, but a lot of the times you should stay consistent with the triangle in the alphabetical order. CA, lastly, or even AC, but CA, just because I'm going in a little bit of a circle here, corresponds with EF, and they are equal to one another. Now, congruent triangles. There is a symbol that we use for congruency, and it's an equal sign with a squiggle on top. That's the congruent symbol. So instead of writing triangle ABC is congruent to triangle DEF, what we would say or write is triangle ABC is congruent, we do that symbol, to triangle DEF. Okay? Now, a lot of the times, congruent triangles, they might not be side by side the same orientation, right? They could, like, one could be like that, and then the other one would be like this, right? And you'd have A, B, C, and let's just say, for example, X, Y, Z, right? You might have something like that, where we can tell that, you know, the longest side length here is AE, and that would correspond to XZ, right? Sorry, AC, looked like an E. And also at the bottom here, you know, BC would correspond to YZ or ZY, whatever we're talking about, same one. AB corresponds to XY, things like that. So, you know, this is a great example of congruent triangles, but sometimes maybe in the textbook homework, they might not be at the same orientation. They might be flipped or rotated, like one triangle to the next. But essentially, folks, congruent triangles, it's literally the same, exact same triangle. Maybe just at a different orientation, or like curved a little bit, rotated or flipped or something like that. But it's basically just the same triangle 2 times, and you probably already knew that. Now, similar triangles. Similar triangles is it's similar to congruent triangles, but they're clearly not. Like, if you look at this example down here, you can kind of see that they're not the exact same triangle. So, a pair of triangles, similar triangles, is a pair of triangles that have equal corresponding angles. Okay, equal corresponding angles. And then it says here, and proportionate corresponding side lengths. Okay, proportionate, meaning there's going to be some sort of ratio or some sort of proportion between the 2 triangles, and we will get into that. So let's have a look at this example. It says triangle ABC is similar to triangle XYZ. So let's just say triangle ABC, the angles, let's just pretend it's equilateral, and we got 60, 60, 60, right? Then we have triangle XYZ, right? It's a similar triangle, so they have to have the same angles. And that kind of makes sense because on the diagnostic, we might have learned that similar triangles, it's basically triangles that have the same shape, but they're different sizes. And the only way that triangles can have the same sort of shape is if they have the exact same angles. And in this case, we'd say exact same corresponding angles. And again, it comes back to like, okay, well, angle A would correspond to angle X, right? Angle B would correspond to angle Y. And lastly, angle C would correspond to angle Z. And I know you know what's going on there. It's really easy to see when the triangles are just standing upright, one beside another. Okay, now let's go into the side lengths here. Let's just say on this equilateral triangle, it has side length of, 10. 10 units, 10 units, and 10 units. And on the little one over here, right, it's also an equilateral triangle, we got 2 units, 2 units, and 2 units. Now, depending on how you want to look at it, you could say that triangle ABC, how many times bigger is it? Well, it looks like it'd be 5 times as big, right? Because if you took this triangle over here, this little guy, and you multiplied each of the side lengths by 5, you would end up with triangle ABC. Likewise, if you took triangle ABC and you wanted to go the other way here, and you wanted to make it triangle XYZ, you would have to divide by 5, right? You'd have to take each side length and divide it by 5. So what we can assume or kind of conclude here is that there's a scale factor involved of 5. And the scale factor is kind of exactly what I mean when there's some sort of proportion involved, right? The scale would be like 1 to 5, but we don't really have to write it as a ratio. Let's just say there's a scale factor of 5, and we know that one's 5 times bigger than the other, or one's 5 times smaller than the other. The scale factor is just a total of 5. Great. So that's actually huge. There are some similarities here. So when you see 2 shapes that have, or 2 triangles that have the exact same angles, you got to be careful because it could just be congruent, right? Because they both have the exact same corresponding angles. However, when they're different sizes, that's when you know that they're similar. Okay. Now, when we're talking about similar triangles, there is also a symbol for similar, and it's kind of like congruent, but there's no equal sign there. It's just that little squiggle right there. We call that squiggle, it's called tilde. That's its name. Therefore, we can rewrite the similarity statement. So this similarity statement here, we wouldn't say is similar to, we would just do the little symbol. So we'll say triangle ABC is similar to triangle XYZ. Now, when does similarity exist? Now, this one is going to get the red highlighter. Triangles, because it's that important, triangles are considered similar if, well, there's 2 conditions. One of these conditions, which is probably the most important one, the one that we will see much more frequently than the other, is that if they have two equal corresponding angles. If you see two triangles, right, like one's bigger than the other, and they have two equal corresponding angles, then, well, if two out of the three corresponding angles are equal in any triangle, right, then the third one also has to be equal as well, of course, because that's just the way triangles are, right? They all have to add up to 180. So if two out of the three, are equal, then that third one is also equal, of course. So if they have two equal corresponding angles, they are similar. And they might call that angle-angle similarity. That's like the condition. They say, hey, yes, these are similar because of angle-angle similarity. But also, sometimes you might run into an example where there's absolutely no angles. And you're like, what do I do here? Well, hey, that's when you look at, they got to give you something. They would give you corresponding side lengths. And we would say that they are proportionate to one another, right? So in the example we have above, we would say something like, okay, well, we know that AB, right, this side length here, AB, would correspond with side length XY. So we would say, well, this one corresponds with XY. And then also we could say BC, which is at the bottom here, would correspond to YZ. All right, not bad. And then lastly, CA would correspond with ZX. Now you're probably wondering why I'm dividing them all. Well, let's have a look. Let's fill in the blanks. AB is 10, and here, I'm going to put in these lines here. AB is 10, XY is 2. And, well, I mean, it's all going to be like this. BC is 10, YZ is 2. CA is 10, ZX is 2. And if you notice, right, all of these are going to equal 5. So what we can say is that the corresponding side lengths, right, the ratios between them would all have to be equal. They're all equal to one another. Like, this is a long way of saying, well, have a look. This one is 5 times as big or 5 times as small. Now, this down here might seem like a waste of time because this one's so simple to see that it's 5 times as big or 5 times as small, but it's actually a great method because sometimes it's not going to be 2 or 3 or 4 or 5 times as big or as small. It's going to be like 2.75 times as big, and that's a little bit more trickier to see. So let's go into some examples here of how to prove that triangles are similar. So this is it. This is what we're going to be dealing with in our homework, okay? So let's first have a look at example 1, part A. It says, explain why you can conclude that triangle ADE is similar to triangle ACB. So I'm going to use 2 different colors here, right? Just for a moment. I just want to show you what these triangles look like first. So ADE, go from A to D to E. And this is our little triangle. And then we have triangle ACB, which goes from A all the way down to C to B back to A. So you notice that there's 2 triangles. I know one is within another, but we do have 2 triangles here. And they want us to prove, without giving us any angles or any side lengths, that these 2 triangles are in fact similar to one another. Okay. Well, notice, actually I'm going to bring those back. I like this. The first thing that we might be able to talk about is, well, if this is true here, we would have parallel. Let's just put in some parallel lines here. DE is parallel to CB. Okay? Now, if that is the case, we have parallel lines. Yeah? And with parallel lines comes a lot of angle properties. So angle D, given this, if you see any patterns here, I see an F pattern here. So we could say that angle D is equal to angle C. Right? We can go ahead and write that. Here's our statement. angle D is equal to angle C. And what's the reason for that? What do we call the F pattern? I mean, could you write F pattern here? Please don't. Let's just stick with corresponding angles. Yeah? So that's our F pattern. We know for sure that angle C and angle D are equal to one another. And I mean, we could surely say the same thing about the other side, right? But I just want to show you another trick here. Notice this angle A. Angle A in both it exists in both of these triangles. See, it's ADE and ACB. So you see that the angle A is in both. So we know that angle A must equal angle A because they're both angle A here, and that's because it's a common angle, right? So we can say that therefore triangle ADE is similar to triangle ACB because of angle similarity. I mean, we could have taken the other angles here and said, oh yeah, angle E is equal to angle B, and those would be our two angles if we didn't have angle A. But I just wanted to show you that because that might come up and be a really useful thing to use here. So, part B. Notice we have here ACB and EDB. So we have ACB, yes, on the left here, and then we have triangle EDB on the right there. Okay. Notice that we have isosceles triangle on the left here, an isosceles triangle on the right here. You know, this is 8. This also must be 8, right? That's 2. That also must be 2. Sorry, that's an 8. Okay, so what are we going to conclude out of this one? Notice that we do have parallel lines. Look at that, AC and DE. And to be honest with you, often we will usually have parallel lines. I don't know why these ones weren't there, but we will always have them. So let's kind of talk about what type of angle properties we might be able to see in here. I'm noticing something like this Z pattern here, which tells us that angle A is equal to angle E, right? So let's go ahead and write that. Angle A is equal to angle E. And the reason for that would be alternate angles. It's the Z pattern. Now, again, yes, we could surely go ahead and do the Z pattern for the other side and say angle D is equal to angle C because of the Z pattern. But I do want to show you a little trick here because look at this. Angle B and angle B. Now, it is a little silly to write angle B equals angle B. So sometimes, or actually a lot of the times, what the textbook does is they say, okay, angle, and check this out. They'll say angle ABC. And what do they mean by angle ABC? Well, if you draw from A to B to C, it's the angle. It's usually just the middle one here is what they're talking about, right? So angle ABC, which is really we're talking about angle B, is equal to angle DBE. DBE. And again, we're just talking about the B in the middle there. And that is because of opposite angles. So therefore, we can conclude that triangle ABC, or it was actually ACB, is similar to triangle EDB by angle similarity. Okay? Great. Good. This is good stuff. So essentially, what we're using is the property of angle similarity to prove that these triangles, or the pairs of triangles, are similar to one another. Because if all the angles are equal to one another, the corresponding angles are equal to one another, then yes, we do have similar triangles. Now, let's throw a situation in that it doesn't give you any angles, and we can't even use angle properties. We can't. There's no angle properties here because the triangles are separated from one another. So, what we're going to have to do is kind of, well, it says these two are, explain why you can conclude that RST is similar to JKL. Well, this is where we're going to have to use the side lengths. So let's try to find matching corresponding side lengths. So RS, I'm going to do in yellow. I think ST, I'm going to do in green. And TR or RT is going to be in purple. So if you have a look at the other triangle, it's like, okay, which side length corresponds to RS? Well, I think it would be JK. Would you agree? I think you would. And which side length corresponds to ST? I think it'd be KL. And lastly, which side length corresponds to TR? Like, oh, wrong color. It's LJ. Now, some of you might be jumping out of your chair saying, oh, I see the pattern, I see the pattern, I can see it, I can see it. Absolutely. Now, I just need you to get into the habit of writing the corresponding side length ratios. Let me write that down. Let's state the corresponding side length ratios. Because we know that if the ratios are equal to one another, it just means that the triangles are proportionate. So I'm going to go ahead and I'm going to put a little box over here and just remind myself that I'm going to have triangle, whoops, that's not much of a triangle, triangle RST on the top of the ratio and triangle JKL at the bottom of the ratio. And that's just going to keep things consistent throughout comparing the side length ratios to one another. So, for example, let's start off with RS. And again, I usually just go in alpha order. RS corresponds with JK. Not kidding. ST corresponds with KL. And TR corresponds with LJ. Now what we're going to do, now that we've kept it consistent, right? This is all triangle RST. This is all triangle JKL. If you ever flip and flop the triangles, you might mess this right up. So try to be consistent. Always be consistent. One triangle on top, the other triangle on the bottom. It doesn't matter what order, what's on top, what's on bottom. Personally, I like to put the bigger one on top, smaller one on the bottom. You might see why at the end here. Now let's fill in the blanks. RS, so let me just get this ratio here. This little symbol here. So RS is 12 centimeters, so that's 12. And then JK is 4. ST is 15. KL is 5. TR is 18. LJ is 6. Okay. Now when we divide these things, I'm going to go to my calculator. 12 divided by 4 is 3. 15 over 5 is equal to 3. And 18 over 6, 18 divided by 6, is also equal to 3. So notice the scale factor here. Let me go ahead and write this down. The scale factor is 3. So we can say with confidence, therefore, triangle RST is similar to triangle JKL because the, say, corresponding side length ratios are equal. They're all equal to 3. I'm going to go ahead and put in my little triangle. Try my best to put in my little triangles here. Okay. Folks, this is the first day of similar and congruent triangles. Your homework is here at the bottom of the page. There's not much there. There's some great questions in there as well. If you do have any questions, please feel free to let me know. But similar triangles, it's a really short unit, and there's some good stuff in here. If you need anything, let me know. Enjoy.